Welcome to this coding problem walkthrough. Today, we'll be exploring LeetCode problem number 940, titled Distinct Subsequences 2. In this problem, we'll work on counting distinct subsequences of a string efficiently. Let's dive in and explore the approaches to solve it. In this problem, we are tasked with finding the number of distinct non-empty subsequences of a given string S. Since the result can grow very large, we will return the answer modulo 10 to the power of 9 plus 7. The input is a string S consisting of lowercase English letters, and the output is an integer representing the count of all distinct subsequences. For example, if S is ABC, the output is 7, as there are 7 unique subsequences formed from the string. To understand this better, let's look at the distinct subsequences of the string ABC. These are a, B, C, yb, AC, BC, and ABC. Each of these is unique and non-empty, giving us a total of 7 subsequences. Now, consider another example where S is ABA. This time, the output is 6. While A appears twice in the string, we only count it once because we are interested in unique subsequences. For the string ABA, the distinct subsequences are A, B, AA, AB, BA, and ABA. Notice how duplicates, like the second A, do not contribute new subsequences. Next, take the case where S is AAA. Here, the subsequences are simply A, AA, and AAA. Since all characters in the string are identical, the number of distinct subsequences is limited to 3. Let's summarize the constraints and some key edge cases to consider. First, for strings of length 1, like S equals A, there is only one distinct subsequence. When characters repeat, such as in S equals AAA, the unique subsequences are A, AA, AAA, and AAA, which totals 4. For strings with all unique characters, like S equals ABCDFG, the number of distinct subsequences grows exponentially as each character adds new combinations. Finally, to handle very large strings, we must compute the result modulo 10 to the power of 9 plus 7. This ensures that the output remains manageable and prevents integer overflow. With these constraints and examples in mind, we are ready to dive deeper into the solution approach. To solve the problem of counting distinct subsequences, one approach we could consider is the brute force method. The intuition behind this approach is to generate all possible subsequences of the string and count the distinct ones. For implementation, we can use a set to store each subsequence, ensuring no duplicates are included. Finally, the size of the set gives us the number of distinct subsequences. However, this method has significant drawbacks. Generating all subsequences takes exponential time, 2 to the power of n, where n is the length of the string. On top of that, storing these subsequences in a set requires a similar amount of space, making it impractical for larger strings where n could be as large as 10,000. This exponential growth in both time and space renders the brute force approach computationally infeasible for real-world scenarios, especially as input sizes grow. So, while straightforward in concept, this method is not scalable and fails to meet the problem's constraints. A more efficient solution comes from the dynamic programming approach. The key insight here is that every subsequence can either include or exclude the current character, which allows us to calculate the number of distinct subsequences iteratively. To do this, we define dp, I, as the number of distinct subsequences that can be formed using the first I characters of the string. For each character, the number of subsequences essentially doubles because each existing subsequence can either include or exclude the new character. However, if this character has appeared before, adding it again would create duplicates. To handle this, we subtract the number of subsequences that were added the last time this character appeared. To implement this, we initialize dp, 0, to 1 for the empty subsequence, and we use an array called last to store the last occurrence of each character. At each step, we update dp, I, by doubling dp, I1, and then subtracting any duplicate subsequences caused by repeated characters. Finally, we return dp, n, 1 to exclude the empty subsequence, and we use modulo 10 to the power of 9 plus 7 to handle large numbers. This approach drastically improves efficiency, with a time complexity of O(n) and space complexity of O(n), or even O(1) if we optimize the dp array. The dynamic programming approach can be further optimized in terms of space usage. Instead of maintaining a full dp array, we can use just a few variables to track the necessary state. This is possible because each dp I only depends on dp I1 and the last array, which tracks the most recent occurrence of each character. By storing dp I1 in a single variable and updating it dynamically, we reduce the space complexity from O(n) to O(1), excluding the space required for the last array. This optimization makes the solution even more memory efficient while preserving its correctness. Ultimately, the dynamic programming approach is chosen because it balances time and space efficiency. The brute force method, while conceptually simple, is computationally prohibitive due to exponential growth in both time and space. On the other hand, the dynamic programming approach leverages overlapping subproblems to achieve a linear time solution, making it scalable for large inputs. Additionally, the space-optimized version minimizes memory usage, though it requires careful implementation to avoid errors. By applying the doubling principle and subtracting duplicates, this approach ensures an efficient and correct solution to the problem, making it the best choice for handling large input sizes within the given constraints. The problem is to count all distinct subsequences of a given string S. A subsequence is formed by deleting any number of characters from the string, while maintaining the relative order of the remaining characters. For example, if S is ABC, subsequences like if BC and ABC are valid. To tackle this, a brute force approach involves generating all possible subsequences using bit manipulation. Each integer from 0 to 2 to the power of n1 is treated as a binary mask, where each bit determines whether a character in S is included or excluded. For instance, if the mask is 001, only the last character is included, forming the subsequence C. This process is applied iteratively for all possible masks to generate every subsequence. When generating subsequences, we store them in a set to ensure uniqueness. The set automatically removes duplicates, which is especially useful when the string contains repeated characters. For example, two identical subsequences formed from duplicate characters will only be stored once. After all masks are processed, the size of the set gives the total count of unique subsequences. The key insights here are that the number of subsequences for a string of length n is 2 to the power of n, and using a set ensures that duplicates are handled efficiently. However, the computational cost of this brute force method is significant, with a time complexity of O(2 to the power of n for generating subsequences and a space complexity of O(2 to the power of n for storing them. To implement this approach, we rely on two important tools, sets and binary masking. Sets are used to store unique subsequences, as they automatically handle duplicate elimination. Inserting into a set is efficient, with an average time complexity of O(1). Binary masking helps determine which characters to include in each subsequence. By iterating over all integers from 0 to 2 to the power of n1, we use the binary representation of each number to decide inclusion or exclusion of characters in the string. For example, if the binary mask is 101, it means the first and last characters are included, while the middle character is excluded. This approach is straightforward and provides a systematic way to generate all possible subsequences. Let's walk through an example with S equals ABC. The length of the string is 3, so the total number of subsequences is 2 cubed, or 8. Using binary masking, we start with the mask 000, which includes no characters, resulting in the empty subsequence. For the mask 001, only the last character is included, forming the subsequence C. Similarly, the mask 010 includes only the middle character, resulting in B, while 011 includes both the middle and last characters, forming BC. This process continues until the mask 111, which includes all characters, resulting in the subsequence ABC. Each subsequence is inserted into a set, and at the end, the set contains all unique subsequences, A, B, C, B, AC, BC, ABC. The size of this set, which is 8, gives the final output. Certain edge cases highlight the behavior of this approach. For an empty string, the only subsequence is the empty string itself, so the result is 1. When the input is a string with repeated characters, such as S equals AAA, the generated subsequences are A, AA, AAA, and duplicates are removed by the set, giving a result of 4. For a string with a single character, like S equals X, the subsequences are X, resulting in a count of 2. To handle larger strings more efficiently, we can optimize the process by avoiding explicit generation of all subsequences. Dynamic programming offers a way to calculate the number of distinct subsequences directly, and in cases with repeated characters, combinatorics can help compute the result faster by leveraging character frequency. To summarize the complexity of this brute force approach, the time complexity is O(2 to the power of n), as we generate all possible subsequences for a string of length n. Each subsequence requires a constant time operation to insert into the set, resulting in an overall time cost proportional to the total number of subsequences. The space complexity is also O(2 to the power of n), as we store all unique subsequences in the set. While this approach is simple and effective for small strings, its exponential growth makes it impractical for larger inputs, emphasizing the need for more efficient methods like dynamic programming or combinatorial techniques in such cases. The solution uses dynamic programming to calculate the number of distinct subsequences of the given string S. The primary focus is on maintaining a running count of subsequences and efficiently handling duplicate characters using a dictionary. ###explanation. 1. Initialization. The modulo constant 10**9 plus 7 ensures the results fit within the allowed range. A DP array of size n plus 1 is initialized, where DP, I, represents the count of distinct subsequences up to index I. The base case DP, 0, equals 1 accounts for the empty subsequence. 2. Tracking last occurrences. A dictionary last_seen is used to store the last occurrence of each character. This helps determine when a character was last seen, allowing us to handle duplicates. 3. Dynamic programming. For each character, we double the count of subsequences from the previous step, DP, I1*2. This accounts for all subsequences that either include or exclude the current character. If the character was seen before, we subtract the subsequences formed before its last occurrence to avoid double counting. The modulo operation ensures that all values remain positive and within bounds. For final adjustment, after processing the entire string, we subtract 1 to exclude the empty subsequence from the final count. This approach ensures an efficient computation with a time complexity of O(n) and space complexity of O(n), making it suitable for large input strings. Here, we start by defining a solution class with a method called distinct subsec_i that takes a string s as input. To handle large numbers, we define a modulus value of 1,000,007,000. We then initialize the length of the string n and set up a dynamic programming array DP of size n plus 1. The DP array will store the count of distinct subsequences up to each index, starting with DP, 0, equals 1 to represent the base case of an empty subsequence. Next, we initialize a last seen map to keep track of the most recent index where each character appears. This helps us efficiently manage duplicate subsequences caused by repeating characters. Now, we loop through the string, processing each character one by one. For the current character, current char, we calculate DP, I, by doubling the count of subsequences from the previous index, DP, I1, and taking modulo mod to avoid overflow. This doubling accounts for all new subsequences formed by appending the current character to the existing ones. If the current character has been seen before, we adjust the count to exclude subsequences that were already formed before its previous occurrence. This is done by subtracting DP, lastSeen.get, current char, 1, from DP, I, and we ensure the result is non-negative by adding mod before taking modulo again. After this adjustment, we update the last seen map to mark the current character's latest position. Once the loop completes, all distinct subsequences of the string, including the empty subsequence, are stored in DP, n. Finally, we subtract 1 from DP, n, to exclude the empty subsequence and return the result modulo mod. This ensures we return the total count of non-empty distinct subsequences in the string. Here, we start with the string ABC to calculate the number of distinct subsequences. First, we initialize our variables. The modulo value is set as 10 to the power of 9 plus 7 to handle large numbers. The length of the string is 3, and the DP array is initialized as 1, 0, 0, 0, where DP, 0, is 1 because there's always one empty subsequence. The last_seen dictionary is empty initially as no characters have been processed yet. Now, when processing the first character, we calculate DP, 1, as DP, 0, multiplied by 2, which gives 2. Since it is not in last_seen, no subsequences need to be subtracted. We then update last underscore seen to mark that it was last seen at position 1. Next, for the character b, dp2 is calculated as dp1 multiplied by 2, resulting in 4. Again, since b is new, no subsequences are subtracted, and we update last underscore seen to record that b was last seen at position 2. Now, for the third character c, we calculate dp3 as dp2 multiplied by 2, which gives 8. Since c is also new and has not been seen before, no subsequences are subtracted. We update last underscore seen to record that c was last seen at position 3. At this point, we have dp3 as 8, which includes all possible subsequences, including the empty subsequence. To exclude the empty subsequence, we subtract 1 from dp3, resulting in 7. This means there are 7 distinct subsequences of the string ABC. Now, let's examine the string ABA. Again, we initialize our variables. The modulo value is 10 to the power of 9 plus 7, the length of the string is 3, and the DP array is 1, 0, 0, 0. The last underscore seen dictionary starts empty. For the first character at dp1 is calculated as dp0 multiplied by 2, which equals 2. Since it is new, no subsequences are subtracted, and we update last underscore seen to record at position 1. Next, for the second character b, dp2 is calculated as dp1 multiplied by 2, resulting in 4. As b is also new, no subsequences are subtracted. We update last underscore seen to indicate that b was last seen at position 2. For the third character a, we calculate dp3 as dp2 multiplied by 2, which gives 8. However, a was last seen at position 1, so we subtract dp0 from dp3. dp0 is 1, so dp3 becomes 7. This adjustment accounts for the subsequences that were double counted due to the repeated character a. Finally, last underscore seen is updated to mark that it was last seen at position 3. At the end, we exclude the empty subsequence by subtracting 1 from dp3, giving us 6 distinct subsequences for the string ABA. For the string AAA, we follow the same initialization steps. The modulo value is 10 to the power of 9 plus 7, the length is 3, and the DP array is 1, 0, 0, 0. The last underscore seen dictionary is empty. Processing the first character at dp1 is calculated as dp0 multiplied by 2, which equals 2. Since it is new, no subsequences are subtracted, and we update last underscore seen to record at position 1. For the second character at dp2 is calculated as dp1 multiplied by 2, which gives 4. However, since it was last seen at position 1, we subtract dp0, which is 1. This makes dp2 equal to 3. We then update last underscore seen to mark as last seen at position 2. For the third character at dp3 is calculated as dp2 multiplied by 2, resulting in 6. Since it was last seen at position 2, we subtract dp1, which is 2. This adjustment gives dp3 as 4. We update last underscore seen to indicate that it was last seen at position 3. Finally, to exclude the empty subsequence, we subtract 1 from dp3, resulting in 3 distinct subsequences for the string AAA. To analyze the time complexity of the algorithm, we start by noting that the main for loop iterates through each character of the input string, which has a length of n. This iteration contributes O(n) to the overall complexity. Then, we have operations on the last underscore seen dictionary, such as updating the last occurrence of a character or checking if a character exists in the dictionary. These dictionary operations, like lookups and updates, are performed in constant time, O(1) on average, and since each character is processed once, this adds another O(n). Additionally, during each iteration, we update the DP array to calculate the number of distinct subsequences. These updates involve constant time operations such as multiplication, subtraction, and modulo, and since there are n iterations, this also contributes O(n). When we combine all these contributions, the overall time complexity of the algorithm is O(n). Now, let's discuss the space complexity. The algorithm uses a DP array to store the number of distinct subsequences for each prefix of the string. The size of this array is n plus 1, which contributes n to the space complexity. Additionally, we maintain a last_seen dictionary to track the last occurrence of each character. In the worst-case scenario, where all characters in the input string are unique, the dictionary will store all unique characters. For lowercase English letters, this size would be min n 26, but for general analysis, it is considered n. Combining these, the total space complexity is n, as the dominant factor is the linear growth of the DP array in dictionary with respect to the input string length. Let's compare this approach to a brute force solution. A brute force method would involve generating all possible subsequences of the string, which amounts to 2 to the power of n subsequences for a string of length n. After generating these subsequences, additional effort would be required to remove duplicates, making the time complexity of this approach 2 to the power of n in the worst case. This exponential complexity highlights the inefficiency of brute force. In contrast, the dynamic programming solution efficiently reuses previously computed results through the DP array and avoids redundant computations by leveraging the last_seen dictionary to handle repeated characters. This optimization reduces the time complexity to n, a dramatic improvement over the brute force approach. Now let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, where all characters in the string are the same, the algorithm still iterates through all n characters and performs dictionary operations, resulting in n time and space complexity. In the average case, for a random string, the algorithm processes each character once and updates the dictionary accordingly, again leading to n time and space complexity. In the worst case, when all characters are unique, the dictionary grows to its maximum size of n. However, even in this scenario, the time and space complexities remain n. To mathematically prove this, we observe that the for loop iterates n times, and during each iteration, only constant time operations like dictionary lookups and DP updates are performed, leading to a total time complexity of n. Similarly, the space required for the DP array in dictionary also scales linearly, resulting in a space complexity of n. By leveraging dynamic programming and efficient dictionary operations, this algorithm achieves linear time and space complexity. This makes it significantly more efficient than a brute force approach, which would otherwise require exponential time. These optimizations ensure that the algorithm handles even large input strings effectively, providing a scalable and practical solution for calculating distinct subsequences. When solving problems involving subsequences, there are a few common mistakes that can trip you up. First, not accounting for the empty subsequence is a frequent issue among beginners. Remember, the empty string is a valid subsequence, and leaving it out will lead to incorrect counts and missed edge cases. The fix here is simple: ensure your solution includes the empty string as part of the set of subsequences. Another mistake is double counting duplicate subsequences in brute force approaches, particularly when dealing with identical characters. You can resolve this by using a set to track only unique subsequences. Finally, inefficient generation of subsequences is another pitfall, especially if you're using an unoptimized recursive method. This approach has exponential time complexity, which becomes impractical for larger inputs. To address this, consider iterative methods or optimize your recursion to reduce redundant operations. Another common variation to be mindful of is the confusion between subsequences and substrings. It's crucial to understand that subsequences can skip characters, while substrings must be contiguous. Misinterpreting this distinction can lead to incorrect logic in your solution. To avoid this, make sure you have a clear definition of what constitutes a subsequence. Additionally, edge cases are often overlooked. For example, you need to handle strings with repeated characters, empty strings, or very long strings. Neglecting these can result in failing test cases. To mitigate this, always test your solution with challenging inputs like an empty string, strings with repetitive characters like AAA, and very long strings, perhaps up to 10,000 characters. Now, from an interview perspective, understanding patterns is vital. Many subsequence-related problems, including this one, rely on recognizing patterns such as dynamic programming states or combinatorial properties. For example, counting distinct subsequences often involves tracking the last occurrence of each character. Another critical point is to use memory efficiently. Instead of storing all subsequences explicitly, which can be impractical, leverage mathematical formulas or dynamic programming to compute counts directly. It's also important to articulate trade-offs. Be prepared to explain how brute force methods compare to optimized solutions, like dynamic programming, and why the latter reduces redundant computations. Lastly, don't forget to address edge cases during an interview. They demonstrate thoroughness and a deep understanding of the problem. Exploring related problems can enhance your understanding of subsequences. For instance, the distinct subsequences problem, LeetCode number 115, asks how many distinct ways one string can be formed as a subsequence of another. Then there's the longest increasing subsequence, LeetCode number 300, which focuses on finding the length of the longest subsequence with strictly increasing values. Another interesting problem is LeetCode number 792, number of matching subsequences, where you count how many words in a list are subsequences of a given string. Of course, this brings us back to LeetCode number 940, distinct subsequences 2, which requires counting distinct subsequences modulo 10 to the power of 9 plus 7. When tackling these, you might explore alternative approaches. For example, using recursion with memoization allows you to reuse results for overlapping subproblems, improving efficiency compared to plain recursion. However, this approach still has exponential complexity in the worst case, so consider the trade-offs. Dynamic programming is a more efficient approach for solving these types of problems. Here, you can use a DP table where each entry, DP, I, represents the count of distinct subsequences up to the ith character of the string. This method has a time complexity of O(n), which is significantly faster than exponential approaches. While it requires a solid understanding of combinatorial properties, it's highly efficient. Another method to consider is iterative bit masking, which generates all possible subsequences iteratively without recursion. However, this method still has a time complexity of O(2 to the power of n), and can be memory intensive for larger strings. Each of these methods has its strengths and trade-offs, so choosing the right one depends on the problem constraints and your familiarity with the approach. That wraps up our discussion on distinct subsequences 2. Remember, identifying inefficiencies in brute force approaches is the first step toward finding optimized solutions. Keep practicing and exploring new problems, and we'll see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!